Hello, this is part 2 of our descriptive statistics for single attribute discussion. In part 1, we talk about mean, median, mode, variance, so on and so forth. Now, we're going to talk about interval estimation, followed by confidence intervals for mean and median. Then we introduce to you the central limit theorem. And finally, we talk about the Anderson-Darling normality test. As we discussed in part 1, these lectures are not supposed to be formal and comprehensive. Actually, it's not very rigorous, only good enough for you to do your work. So, not sure you understand this Excel function. This Excel function, norm INV, simply help us generate a set of random data under the normal distribution. It takes 3 arguments. The first argument is a value between 0 and 1. So this value is used to generate a data so that under normal distribution, the generated data would be mapped to the first argument. Here we use random. Its value is between 0 and 1. The second argument is the mean value. The third one is its variance or standard deviation. But for our case, it doesn't matter. So this normal INV written in this way would generate a set, would generate a data from the normal distribution with mean 0, standard deviation 1. Because we use the uniform random number generator, therefore the generated normally distributed data is also normal. So we use this function in Excel to generate a data set of 100 normally distributed points with mean 0 and standard deviation 1. In other words, we put this in one cell and repeat it 100 times. Therefore, we have 100 normally distributed data. This data is normally distributed with mean 0 and standard deviation 1. So this is one data set. Then we repeat this generation 10 times. Therefore, it is equivalent to say that we extracted a sample of 100 data points from a normally distributed population. Additionally, we did it 10 times. Now, because we did it 10 times, every time we have a computed, or we have a sample mean and a sample standard deviation. So the question is, because these samples are generated from a normal distribution with mean 0, standard deviation 1. So for each sample, the mean and the standard deviation of each data set 0 and 1. That is our expectation or intuition, because the data point were generated from normal distribution 0 and 1. We hopefully every sample we would have sample mean 0, sample deviation, standard deviation 1. But the answer is no, not really. Now let's take a look at what we get. We have 10 samples. Each sample has 100 data points. So for each sample, we compute its mean This one, 0.001, very close to 0. Standard deviation, 1.091, very close to 1. Its median is 0.1301, kind of different from 0. So we compute the mean, standard deviation, and the median for every data set. As we can see, none of the sample would have a sample mean 0, and none of the samples would have their standard deviation 1. Some are close to 0, like this one, this one, this one, and this one, and this one. But some are not. For example, this one, and this one. Sample 9 has a very large, in terms of its absolute value, 0.248, very different from 0. And its standard deviation, 1.2, very different from 1. Its median, negative 0.338, which is very different from 0. So as you can see, the sample means of the samples are not 0. The sample medians are also different. The standard deviations are different. Now, look at sample 9. Sample 9's sample mean, sample standard deviation, and the sample medians are very different from other samples. So we have our observation like this. The sample means and the sample medians are not 0, but close to 0, except for sample 9, which is a sample mean and sample median, negative 0.248 and negative 0.338, respectively. The sample standard deviations are not 1, but sample 9 has a larger value, 1.209. Therefore, when we take a sample and compute the sample mean, sample deviation, and sample median, they could be different from sample to sample. So suppose you have a large population, say you want to understand the income or household income in Houghton, then you think, let's take a sample of 100 household in a random way. You compute the household mean, income mean, standard deviation, and the median. Then you do a second sample of another 100 household. The computed mean, standard deviation, and median would be different. And this is something you have to remember, because the samples are random. Therefore, the computed mean, standard deviation, and median from a random sample are also random. So here are some thoughts for us to do the next step. Let's say M be the sample mean, which is computed from a sample, and mu be the population mean, which may be unknown. So this is our calculated one. This is unknown one. So M minus mu is referred to as the estimation error. Of course, because we don't know mu, in most cases, the estimation error will be different or unknown. So the question is, a very interesting question, is there an interval that contains 95% or 90 or 99% of all the possible estimation errors? In other words, because M is computed from a random sample, so is it possible that we are able to find an interval, even though we don't know mu? Is it possible that we are able to find an interval which can contain, say, 95% of this estimation error, and only 5% may go outside of this bound? So technically, we want to find a delta alpha, where alpha is 90%, 95%, or even 99%, so that the absolute value of the estimation error would be less than delta alpha. So this is the concept of interval estimate. In other words, unlike point estimate, for interval estimate, we want to find an interval that can contain 95% of all possible estimation errors. So this is the definition. Interval estimation is the use of sample data to calculate an interval of possible values of an unknown population parameter, for example, the mean, median, and so on. A point estimation only provides us a single number, but an interval estimation provides an interval that may contain that single number we obtain from point estimation. But to do interval estimation, we did the so-called confidence interval. So this we did a confidence interval. Then we need a confidence level. 95% could be there, or if we reduce a little bit, how about 90%? And if you want to have very strict 99%, for most of the time, we use 95%. So we will discuss confidence intervals for the mean and the median. How do we calculate the confidence interval for mean? Usually, confidence interval will be named as CI in most literature. Of course, we need to find the CI for the mean. We need the mean, sample mean, the sample deviation, which can be computed from a sample. Now, the standard error for the mean, which is the sample deviation divided by the square root of the sample size n. Then we choose a confidence level. Most often we use 95%. Here is the formula. We have the sample mean here. Now, the lower bound and upper bound of the CI under confidence level 95 is this. M, the sample mean, minus 1.96 times the standard error of the sample mean, which is sample standard deviation divided by the square root of n. The upper bound is mean, sample mean plus 1.96 times sample standard deviation divided by square root of n. So that means the possible unknown mean value of the population would be here to here with a confidence level 95%. So in some way, we may want to say in an intuitive way, of all the computed value of m, the estimation error would be this value. So when we use the estimation error to generate an interval, if we do 100 times to compute a confidence interval, 95% of the confidence interval would contain the mean. So we may have 2.5% with a compute lower one. We also have a 2.5% higher than this bound. For 90% and 99%, and even 99.5%, we use here 1.645 for 90%, and 2.576 for 99%, and 2.807 for 99.5%. Now let's copy the formula here. When you see 1.96, it is 95%. Look at this formula. What do we get? If S is large, this is large, this is small. In other words, if S is large, the confidence interval is larger. So this means larger standard deviation S implies larger confidence interval. That is easily understandable. If your sample has large dispersion or large variation, then the confidence interval has to be large to include this larger variation sample. Now, look at the second one. If n is larger, then square root of n is larger. So ns over square root of n becomes smaller. Therefore, the confidence interval becomes smaller. That is here. Larger sample size implies smaller confidence interval. That is, the confidence is smaller, then the chance it contains to bound unknown population is higher, given the same confidence level. And that is why we always prefer larger sample. Now, finally, larger confidence level implies larger confidence interval. That is, look at here. For 90%, it's 1.6. 1.6, so it's smaller. So when we replace confidence level 1.96 by 2.576, that's 99%. So the confidence interval becomes larger. And if you want to be 99.5%, the confidence interval would be much larger. So that means every time we may have some estimation error. If you want to have that estimation error to be included 99.5%, then that interval has to be larger than a smaller confidence level. So this is the confidence level for mean. Now look at the confidence interval of the 10 samples. Sample 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is a confidence interval of the sample mean. And this is the lower bound of the CI, upper bound of the CI. So as you can see, for sample 9, the calculated confidence interval does not even contain the population mean 0 at all. So as you can see, except for sample 9, all the computed confidence interval contains the population mean. But sample 9 does not. What does that mean? Of this 10 calculated confidence interval, one of them does not contain the population mean. That is, the deviation, the estimation error is so large. And that also tells us confidence level. If you choose small, the population mean may escape. Now, if you change the confidence interval from 95% to 99%, this sample 9 would include the population mean. So hopefully you understand what confidence interval is and why we need a confidence level. The computed confidence interval may not contain the population mean. Therefore, we can only guarantee that of this number of calculations, we have only 95% or 90% or 99% could contain the population mean. But the problem is we don't even know the population mean. So when you calculate the confidence interval, you really don't know whether that confidence interval will contain the population mean. Now, this is the first sample. Let's use the same algorithm. We generate 10 more. So now we have the first 10 samples, and then we generate 10 more samples. In total, we have 20 samples. Now look at this confidence interval. And this one shows the opposite of sample 9. Look at here. Its sample mean is large, away from the population mean. And the lower bound is barely smaller than the population mean. Therefore, of these 20 samples, one computed confidence interval does not contain the population mean. One computed confidence interval almost missed the population mean. This is under the assumption that we know the population mean. But for most of the cases, we don't know. So how do we interpret CI? You may interpret in 3 commonly seen ways. A CI is computed from a random sample. Of course, CI is also random. Most likely, that is 95%, it captures the parameter we are estimating. But there is a chance that 5% it could go wrong. We have seen that. If we choose confidence level to be 95%, so the computed CI would have 95% to capture the parameter we are estimating. But there is still 5% it could go wrong. The second interpretation goes as follows. A CI is the range of values that are plausible for the parameter we are estimating. That is, the value inside a confidence interval are likely the parameter we are trying to estimate. The lower and upper values of computed CI are likely the lower bound and upper bound of the parameter we are estimating. So that means we don't know the population mean if we are doing the mean. So even though we don't know about it, we calculate the confidence interval, 95% of the chance the unknown population that each one of the value inside the CI could possibly be the population mean. The third one is 1/2 the length of the computed CI is likely the maximum estimation error. So this is why in recent years, many papers would require you to report confidence interval of mean or median, the two most likely we want to do. So calculating CI is so easy. Whether you're going to use a program or a statistic package or even Excel, you can easily do that. So remember, providing a CI tells your reader how likely the confidence interval can capture the unknown parameter. Now, we can do mean. Of course, we can do median as well. The question here is, there are several ways for computing confidence interval for the median. So here I choose a simple one. That you can do it by using Excel. There are more complex ones. So let's N be the sample size, Q be the quantile of interest. For median, Q is equal to 0.5. So the confidence interval, a confidence level, under confidence level 95%. The confidence interval for the median is this. It's NQ minus 1.96 times this value. Because Q is 0.5, N is fixed. This value is fixed. So replacing subtraction by addition, we have the upper bound. Now find this interval. Then round both N to the next integer. Next, after rounding, you have J and K. Then the confidence interval is between the J's and K's observation in the ordered data. So use 1.645, 2.576, 2.807 for 90%, 99%, and 99.5% respectively. Now let's take a look at a data set of 20 values. Here, now N is 20. Because we want to calculate the confidence interval for median, so the quantile Q is 0.5. The computed lower and upper bounds are 5.62 and 14.38. Round these two values to the next higher integer is 6 and 15. Therefore, the confidence interval for the median is between the 6th and the 15th data point. That's between negative 0.463 to 0.5158. Remind you, there are other methods for computing CI for the median. You know confidence interval from doing some experiment. It's time for us to learn one more concept, the central limit theorem. Remember, for each sample, we computed sample mean. Because the sample means are also random, as it computed from a random sample. Could this sample mean follows a particularly useful distribution? In other words, we generate 20 samples from a standard normal distribution with mean 0, standard deviation 1. So we have 20 sample mean. Are these sample mean follow a particularly useful distribution? To answer this question is very, very crucial. The answer is yes. The sample mean, we have random data. Therefore, this sample mean, random data also form a distribution, and fortunately, it's approximately normal. It's a very beautiful result. So the mean of the sample mean distribution will be equal to the sample mean. And the sample variance will be equal to the variance of the population divided by the sample size. In other words, you have so many sample means. You compute the mean of the sample means. It should be equal to the population mean. Now, if you have so many samples from the same population, you have from this sample, you can calculate a sample standard deviation. The sample standard deviation is equal to the unknown, the sample variance is equal to the sample variance divided by n. And this is S equal to sigma over n. So this is what we're going to learn. However, to make this answer meaningful, n should be greater than or equal to 30. That is why when you write a paper, analyze your classroom experiments, with 22 students or 20 students. And I'm sure many reviewer of your paper would criticize you, your sample size is too small. In other words, typically, people want to see the sample size must be greater than or equal to 30 so that this answer would become true. Now let's explain why without proving it with a few more experiments. That's easy to do. Remember the rand function under Excel? We could generate 100 sample data points from a uniform distribution on 0 and 1 and repeat it 100 times. So in other words, we generate 100 data points from a uniform distribution. So this 100 data point is uniformly distributed over 0 and 1. That's one sample. Then we repeat 100 times, which means we have 100 samples. Each sample has its own sample mean, its own sample variance, and its own sample median. So let's say we have 100 sample mean, 100 sample variance, 100 sample median. So the mean of this 100 would be 0.498, which is close to 0.5. And median is also close, and skew is 0.235, not so large, but not small, definitely. The kurtosis is negative 0.522. It's a negative. So the kurtosis is not very large, which means the sample mean distribution has a flatter peak, but it could still be normal. So this is what we get from a normal distribution. Now, even though you don't know or don't remember negative exponential distribution, that's fine. There is a distribution very commonly used distribution called negative exponential distribution. We also generate 100 samples and then repeat it 100 times. And the mean of this negative exponential distribution is 1. So we have 100 sample mean, 100 sample median. Then we average this 100 sample mean, we have 1.011, close to 1. We compute the median of this 100 sample median, 1.013, close to 1, good. The skewness is very small, very symmetric. The kurtosis is small. So we may have a feeling that the distribution of the sample means is symmetric. This is small. And because kurtosis is small, it also means the pattern, the peak and the tail seem to follow a normal distribution. Now, chi-square. Again, we generate a sample of 100 chi-square distributed sample point from a chi-square distribution with mean 10 and repeat it 100 times. Therefore, we have 100 sample means, 100 sample medians. So the calculated mean of this 100 sample mean is 10.027, median 10.078. Both are close to 10. And even though the kurtosis is moderate, it's still small. But notice here we have a few outliers, but it's okay. Now, what we did was 100 samples. In each sample, we have 100 points. In each sample, the sample size is larger than 30. What if we reduce the sample size to 10 which is less than 30. A critical value you could be criticized. So the mean and median from a uniform disturbance as usual, still close to 0.5, but kurtosis become quite large. That means it's positive, so its peak is higher than a normal. Its tail is thinner than the normal. Now, switch to negative exponential. Again, we only use 10 data points in each sample. So the mean value is 1.0, okay. The median is 0.9, it's still okay. The kurtosis become larger, and kurtosis is not so large, but the skewness is 0.6, moderate, meaning it's probably not very normal. Now, the previous two seems to be quite good, but look at this chi-square. We only use 10 samples. Well, the mean and medians are still the same. So as you can see, the mean may still be close to the population mean, even though you have fewer samples, as long as you generate it in a random way. So skewness close to 0.5, nearly symmetric. Kurtosis is also small. It means this distribution follows normal distribution quite closely. So we see two sets of experiments. One set is 100 samples, each of which has 100 data points. The second set still has 100 samples, but in each sample, we have only 10 data points. So here is what the central limit theorem states. Usually people will call the central limit theorem as CLT. It states that the sample mean distribution, that is, you get a sample, calculate the mean, because the sample is random, the sample mean is also random. So the sample mean distribution is approximately normal. If the sample size is n is large enough, even though the population distribution is not normal, we have seen that. We generate samples from uniform distribution, negative exponential distribution, and chi-square distribution. None of these three are normal. But the sample mean distribution seems to be quite normal. Here is the sample size has to be large enough, n greater than or equal to 30. So the mean of the sample mean distribution will be equal to the mean of the population distribution. And the variance of the sample mean distribution will be equal to the variance of the population divided by the sample size. So a larger sample size estimates the population mean better. This is a typo. I'm going to make some change. Then we keep talking, the sample mean distribution is approximately normal, and so on and so forth. And we frequently raise the word normal distribution. Now, given the data set, how do I know it is normally distributed? By looking at skewness and kurtosis? Well, sometimes it's not very reliable. So a commonly hypothesis testing to test whether a set of data point is normally distributed is the Anderson-Darling test. Nearly all statistics systems have this test. Usually the input to the Anderson-Darling test is the set of data points. That's a sample. And output is a p-value. We'll explain p-value in some later lecture, but not today. So look at this p-value. If computed p-value or returned p-value is less than 0.05, this is the confidence level, 95%. we have evidence showing that the input data points are not normally distributed. In other words, look at the p-value. If it is less than 0.05, then we have evidence showing that the input data points are not normal. If the p-value is even smaller, 0.01, the input data points are highly statistically different from a normal distribution. Normally, we use 0.05. But of course, if you could get 0.01, it means your data points are highly statistically different from a normal distribution. We will cover hypothesis testing sometime later. Now let's take a look at some example using the Anderson-Darling test. Remember, we did two sets of experiments. One set we use n equal to 100 sample size, and then repeat it for 100 times. Therefore, from each sample, we calculate sample mean. This sample means could be generated from the uniform distribution, the negative exponential distribution, and the chi-square distribution. Anyway, we have three sets of sample mean distribution, one from uniform, one from negative exponential, one from chi-square. Then we fit these three sets of sample mean data set to Anderson-Darling test and examine what the return p-value is. Now look at this one is from uniform, this one's from negative exponential, this one is from chi-square. As you can see, the p-value calculated from the normal uniform distribution is larger than 0.05. This one is also larger than 0.05, and the chi-square set is also larger than 0.05. Therefore, we cannot say these three sample means are not normally distributed. Now, return to sample size n, we have this. The uniform distribution has a p-value of 0.18. Well, not less than 0.05. Therefore, we cannot say it's not normal. But for the negative exponential, this is kind of borderline. The return p-value is 0.052, very close to 0.5. So we have some evidence showing that the sample mean distribution from the negative exponential distribution is on the border, right, being normal or not normal. But the sample mean distribution from the chi-square distribution has a p-value of 0.032. Well, we have evidence showing that the sample mean distribution from chi-square, we use Anderson-Darling test to verify the central limit theorem. Hopefully you understand this. If the sample size is larger than or equal to 30, the sample mean distribution is approximately normal. However, if n less than 30, there's no such guarantee. In fact, the smaller n it is, the higher deviation from a normal distribution the sample mean distribution could be. Consequently, if you do an experiment, make sure that the sample size will be no less than 30, so that the reviewers won't attack you at this point. We will mention this when we do hypothesis testing, but we won't get into this seriously. For some hypothesis testing, sample size less than 30 is okay, but you have to provide a good citation for that, because not all educators are aware of this fact. So if your sample size is less than 30, you have to explain why. Normally, some people may accept the sample size of more than 20, but they have only 10. That is always problematic. So this ends part 2. In part 3, we will talk about how to present your data. That is the visualization part. We will explain some visualization basics. Then we explain what is visualization channel ranking, followed by the box whisker or box plot. We use many examples. Finally, we will end part 3 with some recommended reading. Why we get into visualization? When you get your data, normally people just present a table. Table is just a set of numbers, difficult for people to digest the meaning. It would be much better for you to generate some graphics. When you generate graphics, there has something to remember. Some graphics are better than the others. That is the visualization channel. Some are better than the others. Some are not even worth to be considered. Let me stop here. See you next time. Goodbye.